Welcome to AI Paper Slop. If you're an AI researcher, a machine learning engineer, or, a developer building the next generation of autonomous agents, this one is for you.
Absolutely. It's a huge one today.
Yeah, so imagine this. You have two AI agents, right? You give them both the exact same token budget, the exact same tools, the exact same time limit.
Right. A perfectly level playing field.
Exactly. And one solves a complex coding task perfectly. But the other one, it just spends an hour running in circles, hallucinating the same error over and over.
Just burning through your API budget.
Burning through it. But here's the thing. If you are only measuring raw compute, those two agents look identical on paper. And today, we're looking at a paper that proves exactly why that metric is a total trap.
Yeah, so the paper we're diving into is called Scaling Laws for Agent Harnesses via Effective Feedback Compute. It's by Xuanliang Zhang and a team from the Harbin Institute of Technology.
And here is your 60-second TLDR, so we can just get right into it. For test-time compute scaling with large language model agents, measuring raw expenditure, like the number of tokens, API calls, or wall clock time, is fundamentally flawed.
Completely broken metric.
Right. So to fix this, the authors introduce a new trace-level metric called Effective Feedback Compute, or EFC. And EFC only credits compute if the feedback the agent gets is informative, valid, non-redundant, and actually retained in its memory.
That memory part is crucial, yeah.
It really is, because when you normalize this EFC metric by the difficulty of the task, it predicts agent failure rates with an R-squared of 0.99.
Which is just insane.
It's crazy. That completely crushes raw token counts, which sit at a dismal 0.33, and it even beats those traditional multivariate baselines that try to predict success using complex stats.
Yeah, it really does.
So the bottom line is, test time scaling is not about how much budget you spend, it's about how efficiently your agent's harness converts that budget into durable, useful feedback.
This completely upends the prevailing wisdom in the industry right now. I mean, everyone is obsessed with inference-time scaling.
Oh, for sure. OpenAI 01, everyone's trying to replicate it.
Exactly. The assumption has always been, if you just give a model more time to think, or you increase its loop limit, or just give it a massive token budget, it will eventually brute force its way to a solution.
Just throw compute at the wall and see what sticks.
Right. But the mathematical proofs in this paper show us that this assumption is actually really dangerous. I mean, we've basically been staring at the fuel gauge to determine how fast the car is going and completely ignoring the transmission.
Oh, the fuel gauge metaphor is spot on, because the paper really comes out swinging against those raw compute metrics. Let's look at the actual numbers they found.
Yeah, the data's pretty damning.
It is. They tracked how well raw compute correlated with actual success across various tasks. And like I mentioned, the R-squared for tokens is 0.33.
Meaning 67% of the variance in whether your agent succeeds or fails is completely unexplained by the tokens it burned.
Right. And raw cost is only at 0.38. Even if you count operations or tool calls, it only hits 0.42.
Which, if you're a developer forecasting your API bill, those are terrifying statistics.
Yeah, you're basically guessing.
You are. And the real smoking gun here is their matched budget intervention experiment. This was so clever.
Oh yeah, break that down for us.
So the researchers set up a scenario where two groups of agent runs had perfectly identical expenditures. The token budget was exactly the same, the number of tool calls was the same.
So the mean delta in raw cost between the two groups was literally 0.000%.
Exactly. Zero difference in budget.
So they freeze the budget entirely. What did they actually change to test the impact?
They manipulated the environment the agents were operating in just to change the quality of the feedback.
Okay, so how the system responds to the agent.
Yeah. In the control group, the agent received standard noisy feedback. The kind you usually get from a messy environment like ambiguous stack traces or generic server errors.
The classic something went wrong error.
Right, super helpful. But in the experimental group, they altered the environment to provide targeted valid feedback. So for instance, pointing out exactly which line of code was causing a type mismatch.
And the success rate didn't just inch up, right? It skyrocketed from 0.27 to 0.90.
Same exact tokens, wildly different results.
It's wild. I mean, measuring agent capability by counting tokens feels it's like evaluating how well a machine learning model is training just by counting GPU hours without ever checking if the validation loss is actually going down.
That is a perfect analogy.
Right. Like, you can spend 1,000 H100 hours learning absolutely nothing if your learning rate is 0.
Yeah, generating interaction is definitely not the same as generating progress. When you throw more generation loops at a problem, say you give an agent 50 attempts to write a Python script instead of 5,
Yeah.
you're just creating a massive amount of environmental interaction.
But not necessarily useful interaction.
Exactly. If the agent's harness isn't designed to extract a clear signal from all that noise, all you're doing is paying for API calls while the agent runs in circles.
Just spinning its wheels.
Right. The compute is only valuable if it yields evidence that fundamentally changes the agent's future behavior.
Okay, so we need a new metric to solve this, which brings us to effective feedback compute, or EFC. Looking at the paper, they've structured it as a mathematical event-level equation.
Yeah, they break it down very formally.
Right. So for every step the agent takes, EFC is a scaling constant multiplied by 4 variables, I, V, R, and M. But instead of just, listing these off like a textbook, let's think about this practically.
Okay, let's do a scenario.
Say an agent hits an error while trying to build a web scraper. The very first hurdle is that the error message actually has to tell us something useful. And that represents the I, right? Informativeness.
Yeah, informativeness. It measures whether a feedback event reveals new task-relevant constraints or shows measurable progress toward a subgoal.
So if it just says error 500, that's bad.
Right. If your scraping agent queries a URL and gets a generic 500 internal server error with an empty body, that is an interaction, yes, but its informativeness is near 0.
Because it doesn't help the agent narrow down the search space at all.
Exactly. The agent doesn't know if the URL is wrong, if the payload is malformed, or if the server is literally just down.
Okay, that makes sense. But wait, what if the environment is like a hallucinating LLM judge?
Oh, that happens all the time.
Right, so it might give you a highly detailed, incredibly informative critique of your code that is completely fictional. So that must be where the validity comes into play.
Yes, ground truth is critical here. Validity assesses whether the feedback is rooted in reliable evidence.
Like a real compiler error.
Exactly. A syntax error from a Python compiler or a failed unit test has high validity because it's deterministic ground truth.
You can't argue with a compiler.
You really can't. But conversely, if your agent relies on another language model to review its code, and that second model hallucinates a memory leak that doesn't exist.
Oh man, that's the worst.
It is. The validity of that feedback is incredibly low.
Yeah.
You're injecting high informativeness but 0 validity, which basically just sends the agent on a wild goose chase.
Okay, so we have useful information, and we know it's true. Now we look at the third letter, R, which stands for non-redundant relevance. Let me guess, this penalizes the agent if it just runs the same failing code 50 times.
Spot on. Because in that case, the agent is generating tokens, but it's not generating new information.
It's just banging its head against the wall.
Right. Non-redundant relevance asks, does this feedback address the active subgoal without repeating what the agent already knows?
Got it.
If the agent submits the exact same faulty SQL query 3 times and receives the exact same database error 3 times, the R score for the second and third attempts basically approaches 0.
Even though the error message is valid and informative.
Exactly. The feedback is technically informative and valid, but it is completely redundant.
Which brings us to the final variable, M, for memory update. And looking at this formula, this seems like the ultimate bottleneck.
It absolutely is the bottleneck.
Because, wait, since these 4 variables are multiplied together, if any one of them is 0, the entire EFC score for that computational step is 0, right?
That's the brutal math of it, yes.
So if the agent gets a perfectly informative, perfectly valid, and unique error message from a compiler, but it fails to write it to its scratchpad memory,
Then M is 0.
M is 0. The whole step was wasted compute. That is ruthless.
It's ruthless, but that multiplicative nature is the defining feature of closed-loop systems. Feedback is mathematically worthless if it's ignored or forgotten.
Yeah, that makes sense.
We've all examined agent trace logs where the system correctly identifies a missing dependency on step 2.
Oh, I've seen this.
Right. Forgets to install it, moves on to step 3, and then spends the next 50 steps trying to debug why the application won't launch.
Yes. It's so frustrating to watch.
The formula heavily penalizes that exact failure mode. If your memory retention is 0, your effective compute is 0, regardless of how many tokens you spent.
Okay, that is going to resonate painfully with anyone who has watched their agent loop infinitely. But here's where I get a bit skeptical.
Okay, let's hear it.
The EFC formula is elegant in theory, right? It's easy to calculate informativeness or validity if you, the researcher, know the final answer. But how do you actually measure this in real-world, messy environments where we don't have the ground truth?
It's a great question, and the researchers anticipated this exact problem. They actually tackled it in 3 distinct layers.
Okay, what's the first layer?
The first layer is Oracle EFC. This is used in synthetic, procedurally generated tasks like needle lookup or basic state tracking.
Where they control the environment.
Exactly. In these environments, the researchers basically have God mode. They have access to the hidden states of the simulation, so they can perfectly measure if the agent's current step is moving closer to the true hidden answer.
Sure, but God mode is completely useless for my production app. Like, I don't know the answer in advance.
Right, which is why they introduced the second layer, estimated EFC. And this is designed for semi-realistic coding tasks.
Okay, how does that work without knowing the answer?
The brilliant part is that estimated EFC uses only trace time features to guess the EFC score.
Trace time features.
Yeah, it analyzes the agent's behavioral footprint. It looks at the checker scope, how much of the code base the agent is actively testing.
Oh, I see.
It checks if the agent explicitly references its own previous tool, results in its current prompt. It monitors the scratchpad to see if the internal plan actually updates after an error.
But how accurate can that guessing game really be? Can trace features actually predict success without knowing if the code works?
Surprisingly, yes. Estimated EFC achieved an R-squared of 0.94 in predicting failure rates.
Wow, 0.94.
Yeah. It virtually matched the predictive power of the Oracle EFC. It mathematically proves that you do not need access to hidden states to predict if an agent is on the path to success.
That is wild.
The agent's behavioral discipline basically tells you almost everything you need to know.
You know, that is a massive relief for anyone building real pipelines. You don't need a synthetic playground. You can literally run estimated EFC on your production logs today just by tracking if your agent references its previous tool calls.
Exactly. It's highly practical.
But what about the truly chaotic environments? I'm thinking of something like SWE Bench, where an agent has to resolve a massive GitHub issue. It's incredibly noisy in there.
Oh, SW Bench is a nightmare for agents. And for those environments, they developed the third layer, NRS EFC.
Which stands for?
Non-redundant stable EFC. In SWE Bench, agents frequently repeat errors and deal with unstable observations. Like a test script might output thousands of lines of irrelevant warnings alongside the actual error.
Right, log spam.
Exactly. So NRS-EFC uses trace analysis to aggressively discount those redundant loops. It looks for patterns where the agent repeatedly reads the same file or executes the same failing test without actually modifying the core logic.
Oh, so it penalizes them for getting stuck.
Yes. It filters out the transient interactions and focuses purely on durable, retained feedback.
And how did that perform against the raw compute metrics on SWE Bench?
On these mixed real traces, raw compute metrics had a near zero or even negative fit.
Wait, negative?
Yeah, meaning the more tokens the agent spent, the less likely it was to succeed because it was just spiraling.
It was digging a deeper hole.
Exactly. But NRS-EFC reached an R-squared of 0.89. It works even in the messiest software engineering benchmarks.
Okay, so we can measure EFC in the wild, but that brings up a comparison problem, right?
How so?
Well, if I measure an EFC score of 10, that might be plenty of effective compute to solve, I don't know, a simple math puzzle. But an EFC of 10 is nowhere near enough to fix a multi-file repository issue. How do we compare this metric across vastly different tasks?
You have to normalize it.
Right.
Absolute EFC is pretty meaningless in a vacuum. You have to divide it by the required feedback scale of the task, which the authors define as task demand, or D-task.
D-task. Okay, looking at the paper, it breaks this D-task denominator into 5 variables. But rather than just reading the math, let's think about what actually makes a coding task difficult for an agent.
Okay, let's break it down.
It's not just the bare minimum number of reasoning steps required, which the paper calls L. The difficulty also scales with the distractions, right? I think they call this tool selection entropy.
Yeah, tool selection entropy. It basically measures how many plausible but incorrect tools or actions are available to the agent at any given step.
Right.
So if an agent only has 2 tools like read file and write file, the entropy is low. But if it has access to 50 different API endpoints, grep commands, shell scripts,
then it gets lost.
Exactly. The entropy is high. The agent has to sift through a much larger search space to find the right action.
They also include state tracking demand. Which makes sense, like how much context the agent has to hold in its head simultaneously across multiple files.
Right, working memory demand.
Then there's observation noise, like those massive logs with irrelevant warnings we just mentioned. But I am stuck on the final part of this math.
The verifier visibility.
Yeah. The formula includes a term for verifier signal visibility, but it is 1 minus that visibility. Meaning, if a task has great unit tests, the overall task demand actually drops. Doesn't that imply the agent is doing a lot of work? Why is that a good thing for evaluating capability?
It drops the task demand because the environment is doing the heavy lifting for the agent.
How so?
Think about a task with zero verifier visibility. The agent writes a script, runs it, and just gets a blank terminal prompt. It has to rely entirely on its own internal reasoning to guess if the logic is correct.
Oh, right. That's incredibly hard.
It requires a massive amount of brute force feedback gathering. But if the environment provides a reliable unit test like a compiler that highlights exactly line 42 as the problem on it, the agent requires significantly less EFC to find the solution.
Because it's being guided.
Exactly. The guided search reduces the total demand of the task.
Ah, I see. It's like evaluating an algorithm. EFC is how efficiently your algorithm sorts data, but task demand is the size of the database.
That's a great way to look at it.
Right. Like, you can't brag about having a blazing fast sorting algorithm if you're only sorting 10 rows. And when you take the EFC and divide it by this task demand denominator, the predictive power jumps to that near-perfect R-squared of 0.99.
It creates a universal scale. You can finally compare an agent's performance on a basic logic puzzle directly against its performance on a SWE bench ticket, because you have normalized the compute by the inherent difficulty of the environment.
Okay, so if task demand acts as the database size, how do we actually build a better sorting algorithm? Or, in this case, how do we architect a better agent?
That brings us to harness efficiency.
Harness efficiency. Okay, let's get into that.
Yeah, denoted by the Greek letter eta. It's simply your EFC divided by your raw cost.
Yeah.
It basically answers the ultimate business question. How much effective, durable feedback does your agent's harness extract for every dollar or token you spend on the API?
The ROI of your prompt, basically.
Precisely. And to test this, the researchers built 7 progressive harness designs, scaling from H0 all the way up to H6.
Let's walk through these. I know H0 is just a direct answer, like a single pass, 0 loops, no memory.
Right, the simplest possible setup.
Then you have H2, which is routed tools, where the agent can make API calls, but isn't really great at iterating.
Yeah.
And finally, you get up to H5 and H6, which are deep closed loop systems. These have strong routing mechanisms, rigorous verification loops, highly structured memory, all the bells and whistles.
Right, and the researchers systematically ablated these modules, taking them away one by one to analyze how routing, memory, and verification actually impact performance.
And what did they find?
They discovered that harness efficiency, that eta value, explains the variation in success with an R-squared of 0.97.
Wow.
Yeah. And improving your router quality gives the largest efficiency gain, followed closely by verifier strength and memory fidelity. Expanding the raw context window or the loop limit, it explained almost nothing.
That's crazy. So obviously, if I'm deploying an agent tomorrow, I just use the H6 deep closed loop for everything, right?
Yeah.
I mean, it has the best memory, the most rigorous verification. It should dominate.
See, this is where the paper is truly mandatory reading, because that assumption is actually wrong.
Wait, really? Why?
Because harness efficiency is heavily slice dependent. It depends entirely on the environment.
Okay.
On a benchmark like Human Evil, which is isolated code execution, where you have incredibly rich, reliable verification from strict unit tests, H5 and H6 absolutely dominate. Their efficiency is massive, around 1.9.
Because they can actually use their complex loops to refine the code based on solid, truthful feedback.
Exactly. They get a good signal and they iterate on it. But what happens when you move to SW Bench?
The messy GitHub issues.
Right. The environment simulates messy, real-world software engineering. It rarely offers clean, verifiable feedback. You might run a test script and get a wall of confusing text.
Yeah, total chaos.
On these messy tasks, mid-stage harnesses like H0 and H3 actually perform the best. H6 completely drops off.
Wait, walk me through the mechanics of that. Why does the simpler harness beat the complex one in a messy environment? If I throw an H6 agent at a massive spaghetti code base, what actually happens?
You're basically giving a hyperactive agent a shovel to dig its own grave faster.
Oh, wow.
Yeah. If an environment fundamentally lacks clean, verifiable feedback, a complex, deep loop harness will waste compute chasing noisy signals.
Because it thinks every warning is a critical error.
Yes. It receives a vague warning log, assumes it's a critical error, and starts ripping apart perfectly working code to fix a phantom issue. It overcorrects based on false premises.
That makes total sense.
A simpler approach like H3, which has good stateful memory but lacks those hyperactive verification loops, is vastly superior in that scenario. It takes its shot, remembers what it did, and doesn't get bogged down trying to parse an unparsable error log.
Right.
You cannot just slap a complex agent loop onto any problem and expect it to scale.
That is a fascinating realization. Like, if you are deploying these agents right now, this requires a massive shift in philosophy.
It really does.
You have to stop optimizing your pipelines by just throwing more tokens, higher loop limits, or longer context windows at the problem. You must architect the harness itself. The routers, the verifiers, the memory structures, to maximize the extraction of informative, valid, and non-redundant feedback. You have to design specifically for the EFC bottleneck.
It's a fundamental shift from optimizing for scale to optimizing for signal. And honestly, this raises a very important question, one that I think the entire industry needs to reckon with.
What's that?
If test time scaling is entirely bottlenecked by the availability of valid, non-redundant feedback, are we approaching a hard ceiling?
What do you mean by a hard ceiling? Like, we can't get any better?
Well, no matter how smart our base models get, no matter how many trillions of parameters they have, if we deploy them in environments that fundamentally lack reliable verifier signals or environments that generate massive observation noise.
Like messy legacy code bases or the open web.
Exactly, or ambiguous business logic.
Yeah.
If we put them there, test time compute scaling is going to hit a brick wall. The EFC formula dictates that if validity is near zero, your progress is near zero.
Wow.
So it begs the question, are we spending all our engineering hours optimizing the agents when we should actually be building more verifiable environments for them to operate in?
If the environment can't provide the valid signal, all the compute in the world won't save you. We might be tuning the engine when we should be paving the road.
Precisely.
That is definitely something to mull over the next time your agent is burning tokens in an infinite loop. Thanks for joining us on AI Paper Slop, and we'll catch you in the next one.